Hi, today we're going to talk about thermoregulation. So why do we need thermoregulation? Well, humans are classed as homeotherms. We are warm-blooded mammals and we maintain our body temperature, the core of our body, at 37 degrees. Okay? Now there's a number of reasons for this. One is that we have to maintain our metabolic rate in order for everything to function normally. And with a 10-degree difference, our metabolic rate will change 2 to 3-fold. And that's not really good for physiology. Everything likes to be in homeostasis, and so we keep our temperature as constant as possible. Thermoregulation also allows activity and flexibility. We are motile creatures, we like to move around, sometimes we need to run, sometimes we need to do energetic things, and the temperature of our body allows us to do this. It also gives us flexibility, because if we can maintain our temperature, then we can go into colder environments, and this is one way that humans have been able to colonize virtually all areas of the earth. Our metabolism creates heat, and our metabolism can vary up to 20-fold, and so in order to maintain our body at a constant temperature, we have to be aware of not overheating it. So we have to have mechanisms that bring our temperature down. And our environmental varies, comes to the flexibility part. Sometimes it's cold, you need to warm your body up, and other times it's too hot outside and you have to find ways to cool it down in order to keep this 37-degree temperature constant. And most importantly is that below 15 degrees C or above 44, tissue damage can start to happen. And so in order to avoid this, we keep our body at normal temperatures, which is 37 degrees C. So this is our thermoregulatory system and how we sense and then adapt the environment. So let's sort of start over here, the external environment. Maybe it's cold or hot. Cold, you end up with heat loss, or perhaps you're being very energetic, you're creating heat. This all then comes and changes your body temperature. The thermoreceptors in the skin, in the CNS, they sense these changes and send them down afferent pathways to the CNS. And then the CNS will have a response, and if you're cold, you will produce heat, and if you're hot, you will facilitate heat loss patterns. And this is the general overview of how you then regulate your heat to maintain a constant temperature. So when you talk about heat and thermoregulation, you have to talk about heat exchange. And always remember that heat travels downhill. It will go from a warm place to a cold place. Such is entropy. And this happens going basically when it's hot, you have fast molecular motion, to cold areas where it's slower molecular motion. And the way in physiology, in physics, that heat travels is through these next 4 principles. So the methods of heat transfer: conduction. So conduction is basically the molecular transfer of heat to one molecule or another in the same state, solid to solid, liquid to liquid. Okay, this happens mainly through tissues such as adipose tissue that don't have very good blood flow, and that's conduction. Convection then is the traveling of a fluid over a hot surface. So convection could be wind passing over your skin. Convection is also blood flow passing through or over muscles. And this can be a very rapid form of heat transfer. Then we have radiation. This is generally infrared electromagnetic radiation. And from heat from the sun into the body or out, your body will radiate heat as well. And then lastly we come to evaporation, and this is essentially the skin, the water on the skin evaporating and taking heat with it as the liquid turns into a gas, requires energy, and it'll take heat and it makes you feel cold. Every time you step out of a cold shower, you have this large amount of evaporation, it cools your body down, you feel cold, you reach for the towel. That is evaporation. Evaporation is always losing heat. Okay, the others, heat can go in both directions. They can leave your body or come into your body. Now remember, for convection in particular, that the thermal coefficient of air is like 20 times lower than that of fluid. So if you stand in a cold breeze, that's one thing, but it won't take away as much heat as if you're standing in a cold river. So important heat transfer points to remember: conduction, convection, radiation and evaporation are all involved in heat exchange between the body surface and the environment. So it can be evaporating if you're sweating a lot, or convection as in the cold wind or in a cold water, conduction if you lean on a hot surface or if you lean on a cold surface, and then radiation, you radiate heat out, but also it can bring heat in. Only conduction and convection are involved in heat exchange within the body. So you have this forced convection of blood flow, and you also have then just the conduction of heat through adipose tissue and through the skin and poorly perfused areas. Conduction, convection and radiation can either lead to the body losing heat to the environment or gaining heat. I've already said that once, but remember, heat always flows from higher temperature to lower temperature. So if it's hotter outside, heat is going to come into the body. If your body is hot to the environment, it's going to leave. And then finally, evaporation always causes the body to lose heat to the environment. If there's evaporation going on, then heat is leaving your body. To maintain a constant core temperature, it is required that heat production and heat loss be equal. So the amount of heat you're making is the same amount is leaving, and if you're gaining heat, in order to maintain a constant temperature, you need to find some way of losing that heat. So we come here now to the core shell model, and this is a model of how your body regulates heat, and it has two parts to it. It has the core, which is what is regulated. That is where your heat is generated, and it is the amount of heat that you generate that is generally regulated. So when you're cold, you're going to end up trying to create more heat. When you're hot, then you try and lower your heat production and get rid of the excess. And so that is the M in the middle. The plus M is the heat due to your metabolism. And then the core will have a temperature denoted Tc. And then on the outside of that, you have the periphery, and this is the skin and the subcutaneous fat, and this is not regulated and it's not held at a constant temperature. The temperature of the periphery will be a gradient from Tc on the inside all the way out to Ts, which is sort of your periphery, the temperature of the skin. And then surrounding that obviously is the atmospheric temperature, Ta, and this can either gain heat through radiation or conduction or convection, or lose heat either by those ways or as well by evaporation. So heat flow in the core shell model, we will summarize here. Heat flows between the core to the skin, driven by the temperature gradient. The larger the temperature gradient, the faster it's going to travel. So with Ts to Tc. And varying the cutaneous blood flow can greatly modify the effective thermal conductivity of the periphery. So you have this gradient of heat. Generally, if you're in a cold environment, your Tc is going to be higher than your Ts, and so you have a gradient of heat that's going to leave. But the speed that that heat leaves is going to depend on the effective thermal conductivity of the periphery, and that changes depending on what kind of circulation you have there. Generally, conductive will move slower than this forced convection we have, and so the more that the blood flows through the periphery, the faster, the larger this thermal conductivity is, and the quicker you will lose heat. Heat flows between the skin and the environment, driven by the temperature gradient that is between the atmospheric temperature and the skin temperature. So if your skin temperature is similar to the environment, there won't be a lot of heat loss. But then if there's a large amount of difference between the skin and the environment, you're going to lose a lot of heat, and vice versa. If it's very hot outside and your skin isn't so hot, heat will flow into the skin very rapidly. And this core shell model we talk about has limits, and these limits are that not all parts of the core are at the same temperature. The body tries to keep the core at the same temperature, but there are areas that are slightly hotter than others, as we see when it comes to measuring them. And also the shell is not fixed, or the core is not fixed, I should say. The core will expand and contract as the body sort of modulates how to maintain the thermal conductivity or change the effective thermal conductivity of the shell, and so it expands and contracts. And so this is shown here. In the warm environment, your core is very large as blood is pumped to many parts of the extremity, and your whole core temperature is kept at 37, and this includes a lot of the skeletal muscle. But then in the cold environment, your blood flow is pulled in, your core shrinks, and the shell becomes a larger insulating layer, so that the loss of heat from your core is prevented by altering then not just the thermal conductivity of the shell, but the general size of it. And so here we come to sites of temperature measurement, and we'll talk about three: oral, under the tongue, and then you have rectal, and this typically is about 0.6 degrees higher than under the tongue, and so this shows already how you can have fluctuations in the different sites of measurement, which shows that your core is not totally fixed. Tympanic measurement then, putting a sensor in the ear. This usually detects infrared, and it's generally not only the easiest, but the one that's used most in the clinic these days, because it directly approximates the temperature of the brain, where it is probably one of the most places to look at it. So here shows the differences of measuring temperatures of the body, oral and rectal. You can see that the rectal temperature measurements tend to be slightly higher than the oral measurements, even if you're measuring the same thing. So hard exercise rectally will be between 38.5 and 40 degrees C, or here orally it will be about 38. And the normal range is fairly similar, but again, rectal just slightly higher. Remember that your body has a diurnal rhythm. When you sleep, your body temperature is at its least, and that's probably because you're not producing as much energy as normally, and your thermoregulatory systems aren't working quite so hard. And then when you're much more metabolically active during the day, your core temperature is about 1 degree higher. So mechanisms of temperature regulation. So this is how your body regulates your temperature. You can vary the rate of heat production, and this is your metabolism. So in a cold environment, you're going to increase that metabolism by shivering, and this will keep your core temperature elevated, but also in a hot environment, then you're going to reduce possibly the thyroid hormone, lower your metabolic activity, and lower your heat production so that you don't overheat. You can also vary the rate of heat transfer between the surface and the environment. So your surface being the skin and the environment. If you push blood to the surface in a hot day, then you will tend to lose heat. But then also if you pull heat away, pull blood away, then your skin will be lowered because it'll more be the same temperature as the environment, and so you won't lose as much heat. And then you can vary the rate of heat transfer between the core and the surface, and this is changing the circulation either closer to the skin so you lose more heat, or further away so you have this insulating layer that prevents heat loss. And these are the three main ways that you will regulate your heat. So when we're talking about raising your metabolic rate or altering your metabolic rate, which is the first way we talked about just then, you have these different exercises. So sleeping, as I talked about, very low metabolic activity, 35 kilocalories per meter squared per hour. And then on the other end of it, you've got running, which is about 600. And in between, we have various levels of swimming and bicycling, lumbering, if you're so inclined to do that, standing around. So at the moment, I'm burning about 90 kilocalories because I'm not just standing, I'm talking. But shivering to about 250. So you have these different ways of elevating your metabolic rate that allows you to then modulate your core temperature. And then on to surface heat exchange. So this is between your skin and the environment. So conduction, convection and radiation can either cause the body to lose heat to the environment or gain heat to the environment, and it's all dependent on which is hotter. If it's hotter outside, you're going to be gaining heat. If you're hotter than the environment, you're going to lose heat, and this is shown here. So if the atmospheric temperature is greater than your skin, you're going to gain heat. However, if the atmosphere is less, then you're going to have heat loss. And if it's much less, you'll have excessive heat loss. And the only way to respond when there is an excessive heat loss is to lower your skin temperature so that the skin temperature is as close to the atmospheric as possible, and so it reduces heat loss. And so when your skin is cold and the atmosphere is cold, there's really not much heat being passed. And so this is then affected, as I'll go into in more detail in a second, by withdrawing blood away from the skin and letting the skin cool. The skin is increased by increasing blood flow to the skin, and TS is decreased by decreasing the blood flow to the skin. That's kind of what I talked about. It starts here about increasing blood flow to the skin is going to warm your skin, and then depending on what the atmospheric temperature, that will increase heat loss, and then vice versa. If you pull blood away from the skin, then you're going to reduce that heat loss. When the atmosphere is greater in temperature than your skin, the only way to lose heat is through evaporation. Now, evaporation will still occur, especially if it's hot, and as that water evaporates, it will take heat with it, even though the atmosphere is hotter than your skin. It'll just take energy away with it. And and in this case, the body only gains heat from the environment by conduction, convection and radiation. So your sweat is evaporating off and you're losing heat, but you're also gaining heat as well because of the hot air that swirls around you and the infrared that comes through into your body. Sweat is secreted by eccrine and apocrine glands, are only eccrine glands are involved in thermoregulatory response, and this is controlled by the sympathetic and cholinergic systems. And then the rate of sweat evaporation depends on the humidity and wind velocity. So if it's very humid, you're just going to get wet and it's not going to sweat much, you're not going to lose much heat. But if it's kind of humid and windy, then it is going to kind of pull some air off you. But if it's dry and windy and hot, that sweat's not going to stay in your skin very much and you lose a lot of heat like that. And then insensible evaporation is unregulated and reasonably constant. And this is just the fact that you're always secreting some kind of fluid out of glands and it just dissipates into the air. And it will vary as well with humidity and the heat of the environment, but generally it's about 25 to 30 mils per hour. Okay, so transfer of heat from core to the surface. Now this is all about changing the circulation of the body. So conduction, simple cell to cell transfer of heat, normally much less important than circulation, but it does determine the minimum amount of heat transfer in extreme cold where there is extensive peripheral vasoconstriction. Now what this means is if you pull all the blood out of the shell, pull it away and you have very little blood flow through that, that's about as low as the thermal conductivity of your body will get. And so when it's really cold and you want to conserve heat, all that blood comes away from your fingers and toes. You know, you can feel it when you're really cold, and what you're left with is the basal level of thermal conductivity. But the circulation then is the transport of heat by the circulatory system that's needed to perfuse the body with oxygen, and this will deal with varying levels of heat production. It'll overcome the insulating properties of your fat, and it'll counter non-uniformity of heat production within the body. Different organs produce different amounts of heat because they have different metabolic rates, and so this circulation will dissipate the heat from different organs and keep your core at a more constant temperature. So the cutaneous circulation, it supplies the metabolic needs of the skin, which is normally over-perfused. More circulation than oxygen is required. Warm blood to the skin, this cools the blood in the body because you've now moved the blood outwards, the thermal conductivity of your shell is greater and heat will flow out faster. Keeping the blood out of the skin conserves heat. You just talked about it. When you pull blood away, then your thermal conductivity, the thermal coefficient of your shell is lower, and this will conserve heat because it will be slower to leave the body. Blood flow to the entire skin can be varied by about 100 mils per minute or less, and as much as 4,000 mils per minute in a warm environment. So you have a great scale of change so that you can really respond to the environment. It might be slightly cold, so you'll only pull a bit of blood away, or it might be really cold and you pull it all away and you have about 100 mils per minute in your periphery. Or it could be really hot and all the blood will be flowing, be all red and losing lots of heat. Transferring blood to the skin changes the thermal conductivity of skin. I've said it several times, and that's because it is worth repeating. And the effective thermal conductivity of the periphery or the body is defined as the rate of heat exchange between the core and the surface is equal to the coefficient, the effective thermal conductivity coefficient, times the driving force, which is the difference in temperature between the skin and the core. And so the speed that you will lose heat is dependent on the amount of circulation that's going through it and the difference in temperature. Okay, blood flow to the skin can be varied by vasodilation and constriction, and this happens through venous plexus and arteriovenous shunts. anastomosis. Okay, so now we're getting into the specifics of how the body regulates this circulation. The venous plexus and arteriovenous shunts. And so the body can move things from the periphery or inside by opening and closing these. And dilation of the shunts causes warm arterial blood to be poured directly into the venous plexus and the dermis and epidermis. So when you're warm, these shunts open and the blood flows to the surface and you lose heat to the environment to try and cool your core down. The short muscular vessels of the AV shunts are heavily innervated by the sympathetic nerve fibers. So it's a sympathetic system that's going to be working these shunts. A vasoconstriction of the arterioles, meta-arterioles and AV shunts are under control of sympathetic center located in the posterior hypothalamus. The hypothalamus is the king of your temperature regulation. You do have reflexes around, but it's mainly the hypothalamus that dominates. So your continuous blood vessels also respond directly to heating, so you lead to vasodilation. So in result, you have local responses, but they are in part dependent on hypothalamic control, and control of the continuous circulation is then an integration of the CNS, spinal cord, reflexes and local control, but the hypothalamic control usually dominates. Okay, this graph shows you how the conductance, thermal conductivity of your periphery changes as you raise core temperature. So you have the tympanic temperature here of the core and the conductance, and as you get up to about 36.9, 37, the thermal conductivity rapidly increases with the temperature as the blood moves into the periphery, and that blood flow then really increases the thermal conductivity of the skin. Okay, countercurrent heat exchange mechanism. So this is kind of another way that your body can regulate your temperature, and this is due now to sort of deeper veins, the deeper system. In response to cold, venous blood from the extremities is shifted to superficial and deeper veins called venous commentans. And these are deeper veins that kind of wrap around your arteries, and they will bring the blood inside, and this does two things. The blood in these deeper veins is warmed by the adjacent arteries. So these veins have been out in the periphery, it's got cold, it's coming back into the core, and that's bad. So before it gets to the core, it runs down the length of the arteries and warms up a bit, so you don't lose so much heat because the returning blood is warmed, and at the same time arterial blood is cooled on the way to the surface. So as the warm blood goes out, it gets colder, and that heat is brought back in through the venous, through the vena commentans, and therefore you limit the amount of heat loss. And so the venous blood is warmed while returning to the core. And this is shown here. So on the right we have how it is in a warm environment. You have arterial blood flowing down, and it's at 37 degrees, and it's nice and warm outside, so the blood is pumped back up the veins, and it doesn't really lose that much heat because it's nice and warm, and so you have separation between the circulations. But here in the center, now it's cold. The arterial blood is flowing down, and you can see these venous commentans that spirals around the arteries, and so the warm blood coming down is cooled by this cold blood coming back up, and this cold blood is warmed by the warm blood coming down. And so you, rather than lose that heat to the environment, it's conserved and it's brought back into the center of the body through these venae commentans. Okay, so this is just generally now overviewing how your body responds first to cold, and then we'll go over the response to heat. So normally thermal equilibrium is achieved primarily through vasomotor regulation. So fine-tuning the sympathetic nervous system and cutaneous blood flow. In response to cold, the thermoregulatory system initiates responses to conserve heat and, if necessary, augment heat production. So the first thing it's going to do is the heat conserving mechanism, and the peripheral vasoconstriction occurs, your AV shunts close, and blood is kept away from the surface. So that thermal conductivity of your shell is reduced, heat loss is lowered, and the countercurrent exchange starts activating, and so you don't lose so much heat from the core, and you're conserving your heat. The heat loss is lowered and sweating is inhibited, but this insensible evaporation still occurs. And if that's not enough, then you're going to increase your heat production by shivering or voluntary activity, and this will then increase your metabolic rate and warming up the core. And so these two things together, this shivering, this creating energy, and the withdrawal of the cutaneous circulation and the blood flow in these venous comitans, this is how your body conserves heat and maintains the heat of the core. And when you go into a warm environment, not surprisingly, or the excessive heat production as you're exercising, the opposite occurs. So peripheral vasodilation, the AV shunts open, the thermal conductivity of the shell is raised, and you can start letting off a large amount of heat. The heat transfer of the core to surface is augmented due to greatly increased peripheral blood flow. Again, this increases the convective current, it increases the thermal conductivity of the shell, and heat flows much faster through it. And also you have increased evaporative heat loss. You start to sweat, and then now you pick up the amount of evaporation, and particularly if you're moving, that evaporation is going to increase, and so you start to lose heat. Now remember, if the atmosphere is warmer than your skin, the only way you're going to lose heat is by sweating. And it removes heat from the body, but also cools the skin so that the skin is less than the core, and therefore heat can start to leave. Obviously, you have to remember that heat travels downhill, and so if you can make your skin colder than your core, then heat will start to leave your core, and this is why sweating and evaporation is good for lowering your core temperature and stop you overheating. Okay, so the neural mechanisms of temperature control are shown here. Thermoreceptors are located in the hypothalamus, the skin, and elsewhere. The hypothalamus and neighbouring preoptic area of the brain establish a set point. You have a physiological set point that your body tries to maintain the core temperature at. And we'll talk a bit about that in the next couple of slides. Transmission of the error signals to the appropriate effector mechanism controlling shivering, sweating, and vasomotor action will then allow you to respond to whatever challenge it is. So if we come over here, we have the core temperature and the skin temperature, and these are sensed by skin thermoreceptors or core thermoreceptors. And the body will sense an error signal, maybe you're too hot in the core, and then your cerebral cortex will lower your voluntary responses. It will send signals to the hypothalamus and reduce your thyroid releasing hormone, your TSH releasing hormone, and to the pituitary. TSH is lowered, your thyroid hormone is lowered, your metabolic rate reduces, and you lower your core metabolic rate, and then obviously in the skin you start to have the AV shunts happening, you start to lose heat. And then in the opposite direction, maybe your skin is cold and your core starts to drop, the opposite will happen. TRH will be released, TSH will be released, thyroid hormone will increase, your metabolic rate will will increase in order to raise your body temperature, sweat glands will close, your adrenal medulla will release epinephrine so that your metabolic rate will increase and raise the temperature of your core. Your voluntary muscles, your voluntary responses will increase. And so in response to the cold environment, this is how your body then will activate things. And it's in two directions. When you're cold, things will increase, apart from your sweat obviously, which will reduce. And then when you're warm, your metabolic rate will fall and your sweat glands will open. And through these mechanisms, through this mechanism of temperature control, you keep yourself as close as possible to that 37 degrees. Now, the hypothalamic set point. Mentioned it there. It's a very real thing. It's more than just an abstraction. There clearly is an internal reference for a preference of a certain set point, and it can change, and it does change. So in monkeys, they've tested high serum sodium at the hypothalamus, and this increases the set point. So the monkeys start to feel cold, and their core heats up, they start, having a greater metabolic energy. And then low serum sodium does the opposite. It lowers the set point so they feel more comfortable at a colder temperature. High serum calcium at the hypothalamus decreases the set point. Kind of the opposite of what sodium does. And then pyrogens increase the set point. And we'll talk about pyrogens when it comes to fever, which is the last part of this lecture. Dehydration increases the set point, so when you're dehydrated you feel cold because your set point is now raised, no longer is at 37, it'll be 38 or 39, and you start shivering even though the room might be reasonably warm. And then various neurological disorders and injuries can also modify the set point. Exercise also might increase the set point too. So thermoreceptors, you have two, and fairly self-explanatory, not anything too complicated. You have warm fibers, and as the temperature raises they fire faster, and then you have cold fibers, and as it gets colder they fire faster. And so you tell then whether it's warm or hot by these thermoreceptors, and they're naked nerve endings whose firing rate changes based on the temperature. And I just talked about that. Warm fibers fire faster at hot temperatures, cold fibers fire more at colder temperatures. Skin thermoreceptors are distributed non-uniformly over the entire body surface, and then your core internal thermoreceptors are located in the hypothalamus, the spinal cord, and the respiratory tract, the viscera, and the tongue. And so they're fairly well dispersed so that your body has good readings from all kind of areas. Sweating and shivering. Sweating is controlled by information from internal and skin thermoreceptors. Mainly, sweating begins when the core temperature rises above about 37 degrees. And then the sweat glands will open and you'll start to sweat. Lower values of skin, below about 32 progressive, inhibit the sweat production. So if your skin is cold but your body's hot, they'll still shut the sweat glands off. And shivering occurs when your core temperature drops to below 37 degrees. So this is just basically when sweating and shivering is activated. For core temperature greater than about 37 degrees, no shivering occurs until skin temperature is reduced below about 20 degrees. So there's a balance between your core temperature and your skin temperature, and the core is most important. But if your skin does drop too much, you'll start shivering anyway. Okay, heat illness. This is where things tend to go wrong. Alright, so heat exhaustion. This is a feeling of extreme fatigue, usually due to an acute exposure to heat, dizziness and headache, vomiting and muscle cramps, and the skin is pale mainly because I think you've lost water perhaps, and the low blood flow to the skin, but it's clammy because you're sweating. Heat syncope, this is a loss of consciousness because of acute heat exposure, causes mass vasodilation, lowers your blood pressure, and you just kind of faint. And then, but heat stroke is a breakdown of the function of the CNS. You've been too hot for too long, and the hypothalamus now doesn't really know what's going on, and your thermoregulatory centers go into malfunction, and your body temperature rises to about 40 to 43 degrees C. There's absence of sweating because the thermoregulatory centers aren't working properly. This is just too much exposure to heat, and your body isn't thermoregulating itself properly. And then you have this anesthetic hypothermia, also known as malignant hypothermia, and this is where you're on the operating table, you've been given an anesthetic, and all of a sudden your body just cranks up the heat. And this is now thought to be due to a mutation in calcium channels. These lock open and the circuit pump starts working overtime, and because it's working overtime trying to remove all this calcium from the cell, you get this massive release of heat. It's very dangerous. Or sodium dantrolene is what is kept in virtually every surgery room because of this problem. But if you can manage to keep the person cool, then the body seems to overcome it. So termination of anesthesia does not usually stop the development of hypothermia. You just kind of have to keep the body cool and apply dantrolene sodium to inhibit this calcium release. Okay, fever. So this is the final slide. And what is fever? So fever is a change in the set point, and this occurs through pyrogens. And these can either be endogenous or exogenous. Endogenous are going to be cytokines, inflammatory mediators, and exogenous are going to be bacterial, pathogens, viral things. And what they do is they stimulate prostaglandins and cyclic AMP, and this changes the hypothalamic set point. It rises. So your body no longer thinks, I need to be at 37, it now wants to be at 39, 40, 41. And as a result, the body responds as if it's cold. And this is very important, okay? So your body now thinks it's cold in the room, and it will do the things that a cold body does. It will pull circulation away from the periphery, and so your skin feels cold and clammy, but the core is boiling, and so the head feels hot, you know. And so this is how the body, so you have the onset of the fever, lots of pyrogens in the body, and your temperature rises because the set point is now at 49.5. So this shivering and vasoconstriction happens because the body tries to raise the core temperature. It shuts off the peripheral circulation and shivers to increase the metabolic heat to drive that heat up. And then you'll go until the body clears the pyrogens, you get over the infection, or it just dissipates, and then all of a sudden the body temperature drops down, the fever breaks, and the person sweats because now they're trying to cool the body. And so this is what a fever is. It is not a temperature regulated disorder, but it is a normal physiological response to an infection caused by these pyrogens. It's a change in the set point, and your body responds as if it's cold until the pyrogens are gone, and then it cools itself down, and so once the fever breaks, that's when the person starts to sweat.